Hello, everyone. Welcome back. Today I will start by talking about a different method, you could think about it, of depicting and visualizing conservation of energy ideas, and that's by graphing. So far, when discussing how energy changes when there's a specific interaction, what we have focused on is the or the change in a sense of energy from one point in time to another. So we've always chose a specific interval, and we just looked at what was the energy at the beginning, at the start of this interval, and compared it to the energy at the end of the interval. Now, as you will see shortly, when we graph energy, it's actually a much more powerful tool of visualizing conservation of energy, because it will allow us to see how energy changes as a function of time in the entire interval, rather than just focusing on two specific points in time. So it's actually a very useful tool in order to be able to see the behavior of a given system when it's interacting as a function of time. Okay, so let's just quickly again summarize. I know you've already seen this table, but it never hurts to kind of take a step back and think about everything that we have seen so far. So first we started with thermal phenomena, where we looked at thermal energies when temperature is changing, and bond energy when a substance was going through a phase transition, or in the case of chemical reaction. Then we've been focusing on mechanical energies, such as kinetic, that has to do with motion, and then these potential energies, gravitational and spring mass, that has to do with positions. And we also saw some examples in the previous recording of actually mechanical energies transferring back to thermal energies, which is typically the case when there's some kind of friction present. Okay, we also, I have also introduced previously this different way of thinking about conservation of energy. So far we have been focusing on this, that for a closed system, closed meaning that there's the zero on the right-hand side, which means there's no transfer of energy in or out of the system, either by heat or work. So for a closed system, the change in the total energy is zero. And that delta just means the difference between your final and initial state. And it's up to you to choose exactly what is the initial or final state, depending on your interest. Do you want to know the speed of the ball right before it hits the ground? Or maybe if you throw it up, you want to figure out how far it's going to go given some initial speed. So depending on the type of question you're trying to ask, you choose your interval. Now, I also showed you that you can rewrite this equation by writing out what does delta mean. So final minus initial, which just basically tells you that the energy total at some final state has to equal to the total energy in some initial state. So we're basically going from thinking about changes in energy to thinking about total energies. And what this implies, because I and F could be any instant in time, that the total energy is a constant. So it stays the same as long as the system stays closed for that interval. So if we're talking about dropping a ball, if we're neglecting air friction, let's say, that system is gonna stay closed until the ball hits the ground, where it's no longer closed because now it's interacting with the ground. Okay, so what is this total energy? Well, it could be a sum of any of these energies we've introduced so far: gravitational potential energy, kinetic, spring, thermal, and so on. So we will look at some examples shortly, and specifically what we're going to focus on is actually how do we plot these energies as a function of time in the entire interval when the system stays closed. So this is again an example from previous recordings with this bowling ball that was attached to the ceiling, swinging back and forth. And we kind of use this idea of total energy staying constant to see that basically what happens, or another way that we can think about this energy being conserved, is that we think about there's kind of a total amount of energy that's present, here represented by this bucket filled to with a certain amount of energy. Initially at point A, we start with all potential, then somewhere in between A and C, we have half potential, half kinetic, then all of that potential energy goes to all kinetic at point C, where we define that zero, and then back to potential and so on. So although this energy keeps on getting transferred between potential and kinetic, the total is staying the same. Okay, so now let's think about how can we kind of take these ideas and instead of thinking about what is the energy at each instant of time, can we summarize that all in one statement by graphing it? So that's what makes plots very powerful, because instead of writing down a bunch of equations, we can depict it all in one graph. Okay, so let's just focus for simplicity on the swinging of this ball from location C to D. Okay, so what is going on at location C? So what we want to plot is we want to plot energy as a function of height. So height meaning the vertical position of the ball relative to this y equals to 0, what we defined as y equals to 0, which is at the lowest position of the swinging ball. Okay, so when y equals to 0, so this is the plot of gravitational potential energy. So when y equals to 0, gravitational potential energy has to be 0 too, because it's mg times y. And then at its maximum height, which is at location D, it's just going to be some mg times y maximum. It's linear with height, so it's just going to be a straight line. Okay, now what else can we say? Well, let's plot. So one thing that what are the energies involved here? We have gravitational potential energy, kinetic energy, and total energy. And these are the three energies we want to show. Well, let's go to total energy next. Why is that? Well, we could do kinetic energy next and then sum the two. That's one way of doing it. But to do kinetic energy first, you kind of have to calculate the kinetic energy between these 2 points. Another thing that we can do is find the total energy and then use the fact that the total energy is the sum of the two to find kinetic. So that's what we'll do here. So, and why is that a useful thing to do? Because once we know the total energy at one location, we can find it everywhere because we know it's a constant. So where can we immediately find the total energy? Well, we know that at position D, there's no kinetic energy. So if there's no kinetic energy, if at this maximum position, there's no kinetic energy is 0, the total energy is just going to equal to this mg times y max, so the maximum potential energy. So that's kind of the first point that we know, but once we know that point, we know it everywhere. So we can draw this straight horizontal line which exactly tells us that total energy is constant. Okay, so now we know total and potential energy, and again, instead of using 1/2 mv squared to try to figure out the kinetic energy, we could just use the fact that that the total energy is the sum of the two, and solve for kinetic energy by subtracting the total and gravitational potential energy. So what we get is also a linear graph, but kind of a mirror image of this in such a way that whenever any 2 points you choose on the green and the blue line here, they should add up to the total energy. So we can also, think physically, does this make sense? Well, what does this tell us? It tells us that at at position 0 right here, the kinetic energy equals to the total energy, which makes sense. If we go back to our previous graph, we see that at this minimum height of the bowling ball, it's all kinetic energy. And then at its maximum, it's all potential. So kinetic goes to 0. And that's exactly what this plot tells us. As these things get more complicated, you will find yourself doing problems where you have more than 3 or 4 lines to plot. One thing that's important to keep in mind is that, or one thing that you could always do to check is that the kinetic and the potential and all the energies involved always add up to that total. So you have to get that total constant energy at the end. Okay, so just kind of a couple of things to keep in mind when you're doing these plots. So, first you have to think about, okay, what exactly does your total energy consist of? What are the energies involved? Do you have gravitational? Do you have spring energy involved? And so on. Then you want to ask yourself, which energy is the easiest to graph? And by easiest, really what it means is what information are you given? So for example, for the bowling ball problem, we knew about the different heights, so we could start with gravitational potential energy, but that might not always be the case. You will see some problems where going directly to kinetic energy first is what's easier. Make sure you know what you're plotting. So what goes on the y-axis is normally the energy, and that has units of joules. X-axis, it could be height, it could be horizontal position. You will see an example coming up next where it's going to be the horizontal position. So make sure you label your axis and your units. And then another important thing is, what should be the origin? So if you think about it, going back a little bit, we chose the bottom of the swinging ball, like its lowest point, to be y equals to 0, but we didn't have to be. There's nothing physical about calling that value 0. Why, we could have easily chosen the floor or maybe even the ceiling. You'll see an example coming up where I will show you how to do it if we chose the ceiling. And the main idea here is that the choice of 0 does not change your physical situation. So regardless of where you choose that, that origin, what it will change things like the total energy and the potential energy, because those potential energy depends on position. So depending on where you choose the origin, your potential energy will shift. But the physics, the physical phenomena you're describing should not, of course, depend on the choice of origin. Why is that? Because what really matters is how the energy changes from one location to the other. So the point is, if, for example, you're trying to calculate how fast a bowling ball will be at some location, of course, that shouldn't depend on what you happen to define as 0. You should still get the same speed. And why would you get still the same speed? Because the speed at given location depends on how much the height changes from one point to the other. So whether you define this point 0 or that one, what matters is what's the difference in the height when it goes, let's say, from B to C. That difference, that delta y, will still be the same, whether this is 0 and this is 1, or that's 0 and this is then -1, because what matters is that you're taking the difference. But if we want to look at total energies or absolute energies rather than changes in them, then we just have to define some location of origin. And the location that we tend to define, it makes sense to choose a 0, which is just convenient. So, we chose the bottom. It's a convenient choice just because everything then is positive. All the energies above is positive. If we choose 0 up there, then everything will be negative. And you'll see that just for the sake of it, we will look at that example next. So now our goal will be, we'll do two things a little bit different. First, we want to set the 0 up there. So it's still the same bowling ball problem. Nothing has changed except I'm putting some numbers here. But now let's set our origin, or the y equals to 0, at the top, at the location where the rope is attached to that ball. A few other pieces of information are given. Imagine that the length of the rope is 5 meters, and that the maximum height, so kind of how far you swing it before you release it, or how far that ball is going to go, is 1 meter above the lowest point where the ball will be. Okay, so remember, this is y equals to 0, and then this is just going to be the horizontal swing of the ball. And what we will see is, what we're going to plot at the end is the energy is not as a function of height, how high it goes, but as a function of the horizontal position. So we'll get to that last, but first I want you to think about what are the values of maximum and minimal potential energy in this interval as this ball swings, if our y equals to 0 is up there. So remember, what is the equation for gravitational potential energy? It's mgy. And then, of course, to find the actual potential energy, you need the mass of the ball. So let's call it 10 for simplicity, 10 kilograms. And then remember, we use g to be 10 meters per second squared. So, okay, think about this. And let's see the answer. So the answer is C. Okay, so why is that? How come we're getting negative energies? It might seem very strange to you at first to think of energies and the ability of energy to be negative, but it's totally normal because remember, potential energy depends on position. And position is something that's arbitrary. It's measured relative to some arbitrary origin that you choose. So that position could be in the negative x or minus y direction. And that's what happens here. Because we chose our y equals to 0 to be at the ceiling, what does that tell us? What's the lowest position at this location? It's going to be at location -5. So right here, y equals to -5. So, make sure you understand that. Up there before, we said this is 0, so that was 0. But now, if up on the ceiling is 0, if we go below 0, we're going in the negative y direction, and there's exactly 5 meters. So this is y equals to -5, which we plug in here. M times g is 100 times -5 minus 500. So the minimum potential energy is -500 joules. What's the maximum? Well, this is as high it's going to go. Maximum is still its highest location. So that's 1 meter above here. So it means it's 4 meters below y equals to 0. So this location is y equals to -4 meters. So we plug in -4 for here, and we get -400 joules. So if you think about it, when you take the difference, if you wanted to know what is the difference between the potential energy here and here, you would say it's -400 minus -500. So what do you get? You get 100 joules. So if you were to define y equals to 0 here, this is 1 meter, 100 times 1, 100 joules. So you see, it doesn't matter whether you're counting relative to that 0 to that 0. What matters is that the change in gravitational potential energy between this and that location will be 100 joules. You still get the same answer. All right, let's see. Now I want you to think about total energy. So remember, for total energy, it's constant throughout. So what you have to think about is, can you find a location here where it will make it easier for you to find that total energy? All right, so think about this. And let's see the answer, -400 joules. So why is that? Okay, so what's an easy location? Well, you might have thought, okay, let's choose this point. But then here, the ball is moving. So there's potential energy, and then you would have to think about, well, what's the kinetic? So it's not necessarily the best choice. What about up here? Up here, so the total, what is the total energy? First of all, it's potential plus kinetic. Up here, kinetic energy is 0. So we know then the total energy up there, which is, minus 4 meters, is just going to be the potential energy, which we've calculated in the previous question to be minus 400 joules. Kinetic energy is 0 there. So the total energy is minus 400 joules. Once we know it there, we know that everywhere along this path, it's going to be minus 400 joules. Okay, so now we've what did we do? We've calculated our minimum and maximum potential energy, and then we can kind of easily connect it in between. And we also know the total energy, so we're pretty much ready to make a plot, except now what we want to do is make a plot not as a function of height, but as a function of horizontal distance. So what I want to do is I want to plot this entire trajectory going from -3, well, let's think about it swinging like back to +3. So why aren't these no longer? So there's the green one here is the gravitational potential energy plot. So why is it no longer a straight line? You might think, well, potential energy goes as mgy, so it's linear with y, so it should be a straight line. But here we're not plotting y, which is height, we're plotting the horizontal position. So in a sense, we're plotting y as a function of x. So how does height change with horizontal distance? It changes exactly by this shape of the trajectory. So because of that, it's going to take that same exact shape as a function of x. And what are going to be its values? Well, we've calculated already. The minimum is minus 500. The maximum is minus 400. Same, it's perfectly symmetric on this side as it is on that side. So we can plot this one first. Then we can plot the total energy, which we also calculated. We calculated specifically at this point, but we know it's a constant, so it has to be a straight line. And then all we're left with is to find kinetic energy. But what we don't need to, again, go through all of these points and calculate it. We could just use the fact that kinetic energy is the total minus the gravitational potential energy. And you could do that by just kind of choosing some points. So right here, total and potential energy are the same. So when you subtract them, you have to get 0. So there's the 0 kinetic energy. And that's, make sure it also makes sense physically to you. If you go up here, these 2 points, -3 and +3, represent the maximum height. And that's exactly when the ball has reached its maximum position. It has to slow down, stop, turn around, and go back down. So kinetic energy goes to 0. Now, this location is where the kinetic energy is maximum. That's when all that kinetic energy, all the potential energy gets converted, or the biggest change in potential energy. So you have to have the biggest change in kinetic energy, so the maximum speed. But again, you could just take these 2 points and subtract them, minus 400, minus 500, so you get plus 100, so that's your maximum kinetic energy. And then you could just sort of extrapolate the shape, because when you don't have linear things, but some more complicated shape, well, all you know is that the sum of these two, so the kinetic and potential energy, has to equal to the constant. And how do you get a straight line? If you take some shape and what you need to do is basically project an mirror image of it. So it has to have the same type of shape, but reversed. And that's kind of the only way that you can get a straight line out of it. So when you get something more complicated like that, always kind of think back at this. What is the shape of the energy that you know? It has to kind of imitate that shape, but in the mirror image of it. Okay, and then here's just, I'm showing you some calculations already that we've looked at. How do we find the maximum potential energy, the total, and then the kinetic energy from that. And again, the main thing here is, or probably the main complication here, is that the fact that we happen to choose our 0 at the ceiling. It might not be the most natural choice of 0, but there's nothing wrong with it. the point is that wherever you choose your zero, you should still get that same kinetic energy, because it's the kinetic energy that tells you about the physical motion and speed of the ball, and that should not matter depending on the zero you choose. So what I suggest for you as an exercise is try to make that same plot, but choosing a different zero. You know, go back to making the zero down here, or maybe you want to say, well, the floor is another 3 meters below. What if you choose a zero there? How would these plots look? You should still get that same kinetic energy. You will do a very similar exercise with a ball falling in discussion lab. So you'll have plenty of practice making these plots given these different choices of zero. All right, thank you for listening. Bye.